Good afternoon, everybody, and welcome to the third of our SCItalks. This one is particularly interesting. The sort of the idea of how digital technologies can revolutionize manufacturing has been around for quite a while now, but over the last few years, it's gained its own reputation as the fourth industrial revolution and things like that. And so this afternoon, we're going to be led through this area by a person who's been in it for a long time. So welcome to the Myths and Realities of the Manufacturing Digital Revolution by Robert Harrison. What Robert's going to do is explore what's going on in this, what the fuss is about, some of the things that are true, some of the things that are not true, how the real world interfaces with the digital world and so on, and how we're changing the way we think about factories, plants, supply chains, and the whole thing. My name is David Bott. I'm the chairperson. At the end of this talk, which will last 50 minutes to an hour, there'll be a Q&A system, and that will be coordinated by Tom and Heather, whose pictures you can see here. Robert is the Professor of Automation Systems and Head of Digital Technologies Directorate at WMG. He's been around this field for a long time, and he explains it very clearly and coherently, and he's been known to explain it not just to manufacturing people, to healthcare people and to farmers and all sorts of things. Robert is truly experienced. He before WMG was at Loughborough. He's worked with most of the major manufacturing companies around the world, doing all sorts of interesting things and tackling the sorts of problems that come up when you try to apply digital technologies to manufacturing processes. He's incredibly well connected, incredibly nice bloke, and it's my great privilege to hand you over to him now. Robert.
Thank you, David, for that kind introduction and the opportunity to be able to talk today. Topic today is that, as David said, myths and realities of the manufacturing digital revolution. Again, as David said, I'm a Professor of Automation Systems at WMG at Warwick. Just very briefly, for those of you who may not know WMG and Warwick, just a few general points on this first slide. So we're a department of the university, Warwick University, and we've expanded greatly over the last number of recent years. We were founded by Lord Bhattacharya in the 1980s, who built up our centre. So we're very much a part of the university, and also, as come on to on the next slide, we're one of the 7 high-value manufacturing centres in the UK. So really, we're in quite a unique position in terms of being both an academic department and a member of this catapult organisation. So we really truly span, from early research through to commercialisation and industrial impact. The manufacturing digital revolution. Well, I think, as everyone is aware, really, digital technologies are now impacting on life generally in many ways, and in the context of this talk, the way manufacturing operations are carried out. Again, I think, as David mentioned, that the term Industry 4.0, fourth industrial revolution, that's very much a trend now in automation, and that only combines several technologies I'll talk about, and also in particular interconnectivity and real-time data. So it's the amalgamation and integration of technologies, as well as their individual, perhaps disruptive capabilities and impacts. There's also a perspective which is the integration of digital technologies with physical manufacturing systems, or what are known as cyber physical production systems, and at any rate in this context. And the picture on the right hand side of the slide shows some examples of that, where there's a virtual image of an autonomous robot and a production system, and its physical twin in an environment where you can also display analytic and KPI data overlaid onto those scenes in a concurrent manner. In terms of why and what are these enabling digital technologies and capabilities for? Well, I think this slide created by Corin shows perhaps quite well the trends from craft production, where you could have plenty of variety in a product, through to mass production, where you basically got one as long as it was black, if you like, in terms of Henry Ford, but you got reduced the cost whilst limiting the product variance. And now, coming back around the curve, that movement through mass production and globalization to being able to have more personalized products. So, from a volume and cost perspective, moving through to, customization and the user experience, and perhaps even more so now, not only having, flexible systems, but perhaps moving towards more resilient systems where digital technologies can enable a lot more agility and reconfigurability in systems, or there's the opportunity to, to enable and see that. So I think all of you will be aware of Industry 4 as a concept, and perhaps the number of industrial revolutions which the way this has been pitched and described went before it, so from steam power through assembly lines and mass production systems to the automation enabled by computers, and the advent really of digital technologies, if you like, in Industry 3, and then Industry 4 being beyond that base level digital capability, moving to cyber physical systems. I mentioned the Internet of Things, or the industrial Internet of Things in particular, in the area that we're talking about, and connectivity and networking in that context, linking, as we'll see, both IT systems, at the top floor, if you like, down to the production systems at the lower levels, which in the past were really entirely separate. So some key disruptive technologies, and you'll see many perspectives and sort of iterations and diagrams indeed around this, but some of the key nine of the key technologies really shown here in terms of simulation capabilities. We'll see a lot around virtual models and simulation, the vital integration horizontally and vertically of systems, the industrial Internet of Things I talked about, the vital component of cybersecurity in these systems, cloud computing at the higher levels, enabling collective devices broadly to be put together and high levels of computing power brought to bear. Additive manufacture as a local, truly digital manufacturing perspective. Augmented and virtual reality are again important perspectives. And once we have hold of this data, the ability to use it, via analytics is again a key component. And then at the top there, you've got robotics and autonomous systems, because another trend is towards more autonomous, independent, self-configuring systems in this technology perspective. So why are we using and gearing off these digital technologies? Well, obviously this needs to impact business performance as well as the other aspects we've talked about earlier, in terms of perhaps opportunities now for more resilient production systems and flexibility. There are the sort of inherent, aspects of what business models we can deploy. Can we improve production in terms of cost and quality? Can we integrate and reuse what we have? Reduce time to market, which is obviously important, not to reinvent the wheel, but to utilize the models and methods we already have. Again, in the current context, can we reduce waste, run our systems more environmentally sustainably, and connectivity across supply chains? And in the smart factory context, as we'll see, that isn't just a single building, but a network and a connection of various factory entities, and the logistics and delivery systems needed to supply and integrate those. And then perhaps on the right hand side, just to say that that connected enterprise now is requiring and seeing this integration of information technology and the operational technologies on the shop floor. Another way of looking at this, and some of you may be familiar with the pyramid model, the ISO 95 model in terms of traditional factory systems, and another way of looking at this digitalization and Industry 4 perspective is an extension of that pyramid beyond, you know, its traditional facets to add the things on the right hand side, you know, the from lower levels of embedded control and being able to pick up additional sensor data from the industrial Internet of Things, through building data models on top of the basic production system, so that there's there the opportunity to model the physical systems and have ultimately real-time data from them, and then feed that into digital twins of those production entities, and so on. It's vital to have security as we open up, you know, the areas of the system where they were traditionally, you know, closed and separate. Cloud services and infrastructure at the higher levels to integrate and provide the higher level perspectives, and then data analytics, machine learning, you know, AI above that. And then the arrows on the right there, just really to show there are kind of a couple of trends really, which is one towards, you know, centralization, moving things into the cloud to get that bigger collective picture, and the other one is migrating capabilities, including AI, to the edge, so that you can actually do processing on the local devices and then feed, you know, valuable information and insight to the higher levels of systems in whatever domain you might be. So this is really very general and applicable to all domains, from, you know, the process industry, food industries, automotive, aerospace, etc. These are all, you know, generics that I'm talking about in that context. If we just touch on where did the term Industry 4 come from? Well, with the German spelling here, Industry 4 was very much a, you know, a vision initially from Germany with a quite well-defined perspective and quite clearly articulated. So these are some points here that I just thought I'd quickly touch on, because it's interesting really that there's the seamless data exchange and communication, the you know, use of IoT systems, cyber physical production systems to bring in smart machines, warehousing, you know, those production facilities. That coupled with uniquely identifiable products, so each product, you know, knows its history, status, how it's routed through, you know, the production system. And also there was a vision there of, you know, distributed systems, so autonomous distributed systems. So each system can, you know, control and configure itself and adapt to the, you know, to the needs of the current situation. And then again, as we've touched on earlier, you know, smart factories being vertically linked to the operational processes and horizontally linked, you know, more widely in a global in global value networks. So these were, you know, fundamentals that were seen at that time as being, you know, important. And then out of that, just might be interesting to see the kind of amalgamation of these terms, methods, approaches, and another buzzword, if you like, that's gaining a lot of traction, you know, more recently has been around digital twins. So dynamic representations of production systems, which are updated potentially in real time. And in this context, you're able to cross-link between, you know, the digital, not only the operational system, but a digital twin of its production and a digital twin of the product, and then collectively being able to continuously optimize, you know, the product and its production. Again, in whatever domain might be applicable, these digital twins and the underlying models behind them would be different, but the concepts and approaches would have you know, a great deal of commonality in many ways. So moving on to the myths and realities of this digital transformation. I've tried to go through the next few slides, a few of these from some of the perspectives which are often mentioned, and to touch on, I hope, some interesting points. So one's really that does this mean large expenditure? I think really, as highlighted on the slide, it's not the amount of money you spend, but how you spend it. And in a technical context, the costs of these technologies are continually falling, dramatically. And IoT platforms are affordable. Not only the components, but the required services are also available, almost independent of scale for anybody, and globally. So connectivity, cloud-based hosted systems, the use of big data and appropriate application development tools are there, and the market is constantly evolving, and the technologies are moving in this context very, very quickly. So cost isn't necessarily a barrier at all in terms of large expenditure. Again, I think technology is too expensive. Just to reiterate that point, MIT have done some studies, and we're really talking about this orders of magnitude decrease in the costs of what were traditionally expensive sensing, actuating, networking and computational devices. So GPUs and edge computing devices and so on are continually falling in price. There are a number of disruptive partners and companies coming into that market, and also the traditional players are seeing competition from new entrants, using perhaps non-traditional platforms for doing data processing, and indeed, the traditional programmable logic controllers and industrial devices are seeing increasing competition. In that context, managers are still reluctant to invest, perhaps. They want to see proven business value, and this is obviously a fast emerging and moving field. Will automation eliminate jobs? I think it's inevitable that automation will, reduce the need for manual routine roles in manufacturing, and we're seeing, examples of that already. There'll obviously, on the counter to that is that the creation of new types of jobs, and staff capable of working with and alongside these new technologies and methods, will prosper in that context. So hence the importance of skills training, retraining, providing relevant skills to graduates, and continuous through career education. Data, big data. Data is essential everywhere and a fundamental part of Industry 4 and the digitalization initiatives, and that's throughout the life cycle, from the way systems are built and designed through their operational phases to their their reuse and indeed through their use with the customer, because these are all areas of connectivity and integration that can add value and provide services. So data is key. Simply, collecting data is not enough, and we've had numerous examples in our projects where we'll get huge amounts of data presented to us, but it may be incomplete to be able to, solve the problem you want, or of very poor quality. There may be missing aspects of the data. It may be collected in inadequate ways. So data needs to be leveraged, which may initially mean cleaning up and very much understanding that data before you start to try and analyze it and model it. So that's what are often called actionable insights, really. Getting good quality data, and then as a stage after that, being able to look at what it means and derive more and more value from it, and cross-relating different data, be it in that context. And the diagram on the right really showing that this, and a colleague of mine in our group, Dan Vera, would often mention about connect, collect, analyze, react as the the stages really of a closed loop process, and that could happen at all levels in the organisation in terms of meaningful data you're able to collect, cross-relate, and add value to feed back into your operations. The next slide, real-time visibility of data. So we've talked very much about the sort of context of Industry 4, and very much in factory systems, you'll find that they're only able to react after the horse has bolted, in the sense that they're not able to react quickly enough to be able to make decisions in real time. So real-time visibility is very, very important in the context of promoting the full value of digitalization and Industry 4. This is compounded, and it faces people face challenges in the sense of most systems can consist of in truth a mix of applications and siloed data. So being able to combine and obtain real-time visibility from such data is difficult. So this is an aspect of the systems where there are challenges. There may be latency in gathering information, the lack of a real-time view of enough information to fully understand a business status and make relevant decisions. In that context, there are a number of integration platforms and methods. So just in passing as a relevant example, we have a project at WMG, which is just starting with a consortium at the bottom of the page, and a number of our industrial partners and smaller startups and innovative partners to offer a way of integrating this kind of data. So being able to offer the relevant connectivity, be able to broker that data and distribute it to applications in a single ecosystem. So these kinds of approaches and systems are really important in terms of being able to provide more real-time visibility, decision making, and also integrate applications throughout the the life cycle of such digital systems. So that's integrating those technologies and enabling bigger data models and different tools and methods to be used at different and appropriate phases of the design, operation, and reconfiguration indeed of production systems. Another general context of how to succeed in this context, and this is again an evolving, very much evolving and disruptive marketplace for those involved in it. Really, it's often not who has ultimately the best technology, but who's able to adapt, adopt, and offer the technology in a way which enables it to be easily used. So help manufacturers to adapt and adopt the technology to be able to transform the dynamics of their systems. Suppliers to be able to provide products that are easy to be used by those manufacturers, and in the context of their existing system. So make it easier for the customers to make that move to digitalization. Again, talking about the sort of stages and phases of the digitalization process. You need to do this, stage by stage, and the foundations obviously are as we mentioned before when we said connect, analyze, react. Being able to have digital systems, being able to connect to them, be those IoT sensors or existing legacy machines or adding vision systems, etc. There's then seeing and understanding what's happening in terms of the visibility of information really from that data, and then building on that to offer predictive capacities and adaptability in terms of ultimately, as we talked about, systems being more autonomous, them being self-optimizing, and ultimately being able to adapt as conditions change without having to report upwards, because the classic traditional manufacturing systems would be optimized with tools which would assume a certain state for the system, but in truth that optimization would rarely occur. Systems would run suboptimally, there will be many changes occurring, and so the ability to systems to self-optimize, although they ultimately may not be running at the efficiency you might have seen for that idealized case, in practice they will be much more resilient, much more agile, and much more able to adapt and have less central points of failure if they are more autonomous. So now, having talked about a few of those perspectives in terms of myths, realities, and the background, I thought I would turn to look at some examples of what we're doing at WMG in creating this kind of pathway to digitalisation. So in that context, our work, and I talked about the department being a department of the university and a catapult centre. We'd look at this from the points of view of proof of concept systems, demonstrators, make-like production facilities. We have a number of these, particularly in the area of electrification, the HFEMs and Amplify projects at Warwick, and then going through to factory installation. So there's that breadth and this idea of a pipeline or pathway to take new technologies through to full industrialization and to have industrial impact. Another perspective on this is, and again linking into the sort of aspects I talked about in terms of technologies, is some examples here of making use of Raspberry Pis and innovative low-cost technologies, augmented reality using tablets, mobile apps, again on tablet-based devices. The impact of gaming technologies in this context, simulation and modeling tools, and ultimately, obviously, physical production systems at different levels, from benchtop demonstrators through to full automation demonstrators and pilot production systems, as I talked about in the last slide. So this is the span of automation systems group research at WMG, and that is just one facet of the Digital Technologies Directorate, which more broadly looks at cyber physical systems from the security perspectives, big data analytics perspectives, visualization. There's a digital lifecycle management group again, which is a very important aspect of this context. And then now, just taking that a bit further, wanted to touch on some examples. So again, as I've mentioned already, obviously manufacturing is far from optimized. We see volatility in demand and unforeseen disturbances in the supply chain. So how do we react and cope with those? So an area we've been pursuing quite a lot is this term of dynamically adaptable systems, and also in the boundaries between subsystems, you tend to get a lot of inefficiencies. So one example is integrating logistics with production systems, dynamically being able to reschedule, flexibility in those systems, and being able to track products and services and products and production systems as they operate. One company, which I'll show in a couple of the examples going forward, is Lear, who make seats in the automotive sector. So here you've got a generally highly manual production environment where seats are built to sequence, actually, interestingly, and each seat is potentially highly customized. So they may be not only different colors, but have many different features in terms of color, whether they've got heating, cooling, massage. The top end vehicles, it's a very high quality, high value item in that context. And Lear, an example of a company with global facilities in manufacturing this type of product. In these kind of examples of production where you're moving products around in many different small batches, or having to make, in a sense, batches of one of each color, but build to sequence in a high volume, context, you can end up with a lot of non-value add while you've got sub-assemblies being brought together, and so on and so forth. And so very often there's quite a bit of non-value add time in there. So this has been non-productive aspects of what's being done, be that inspection, work which shouldn't happen due to rework, and so on. So we have looked at some aspects of this in particular with regard to integrating people and production machinery, and as I say, I mentioned about adding and integrating logistics with assembly operations to give a more adaptable and holistic approach. So we've been prototyping, and again, an area very much of digitalization is in the engineering tools, where much of the prototyping work and indeed verification and early validation of the systems can now be done digitally before the physical systems are built. So in this example, we've been looking at standard kitting boxes, which are used throughout Lear's production facilities, and been looking to, instead of having a centralized warehouse, have localized distributed warehousing and local kitting systems. So just an example here to show this idea of a local warehousing system and being able to move products in that context locally, and then adding autonomous vehicles with laser scanners to be able to transport those around the shop floor. So in the Lear shop floor, you would see a huge shop floor area with many boxes of product being handled in racks all around the production facility. So being able to move those in a more controlled, measured way, to track exactly where every consignment is, and to be able to develop new manufacturing equipment in that context, as well as the digital, underlying digital technologies, is a key aspect of what we're doing with them. So these are moving to more and more agile and flexible automation. So again, in this slide, shows an example. There's a little bit of animation on it on the right hand side, showing an example of being able to introduce cobots to the manufacturing processes. So again, working and assisting the workers, where on leather seats for automotive vehicles, as you'd imagine, each hide is a unique one which came from a different animal, and it will have different defects, and when the seat is made up, different bagginess or rework, as they would see it, finessing as they call it, to complete that surface properly to a high quality standard. And we've been working with Lear to look at how we can digitally measure the quality of the seat, and through machine learning and the use of AI more broadly, to be able to analyze information from vision systems and then automate the seat finishing processes. On the left-hand side of this slide, there's other innovations we've been doing, which are linear drive conveyor systems, where again, these are digital devices which are completely reprogrammable. So instead of having rollers and belts, we've got a linear drive, and there's a digital position for every pallet, throughout its manufacture. This next picture is again a 3D simulation, and when I run it, you'll see some other aspects of the sort of concepts and methods we're developing in terms of greater autonomy in the manufacturing systems, combining the sort of analytics capabilities I've talked about, and collaborative robots. And in this vision, this is just showing future concepts in a sense, but the thrust of this work that we're working with Lear and with other companies in this future digitalization is smart factories, where in this context you 100% automate the manufacture of the car seats. So the technologies here relate to the every phase of the digital journey, if you like, through the life cycle of such systems, in that we can shift a lot of the design work and conceptual engineering into the digital space, and then feed data back to those models to be able to use them as visualizations and through underlying data models and what have you, they become a digital twin of the the production system. There's another example here I can show you where we need to track tools on the shop floor in real time. Again, there are crossovers here with what you would see in indeed the medical area in tracking operations. We're using similar technologies, but here we're using optical digital tracking technology to track the position of a tool in space, and that's integrated with digital work instructions, and it lets a validation process be carried out, so we know exactly which fastener has been tightened up, in what order, and we know not only the torque and angle from the the tool, but we know where that tool was in 3D space. Now, this is similarly in the past been done with like pantograph arms and what have you, but they were very unwieldy. So using either active or passive markers, we're able to track this, the movement of that tool. We know which operator was doing it, and the seat has a unique identifier. So track and trace of the product is integrated with an understanding of what the production operations, were done and by whom and at what time. And this is obviously critical in the sense of there are safety critical components on a seat, such as the airbags and so on, which make this very valuable, not only from the productivity and optimization of production standpoint, but from the the safety and quality perspectives. Another example relates to delivery of, in this case, rivets around the shop floor. So self-piercing rivets are used by Jaguar Land Rover, for example, and Ford in the manufacture of aluminium-bodied vehicles. Those rivets are normally sent manually to each of the riveting stations, and we've done some work around automating these kinds of delivery processes. And again, to fulfill that, you need to integrate with the warehousing system and with the the manufacturing cells on the shop floor. So this is essentially like a milk round, delivering the full rivet containers and taking away the empties. So again, you'll see the prototype here, which has been developed by our automation systems group. And again, there's an integration of a number of different technologies here, in the sense of using machine vision. The grippers here were additive manufactured. It uses a cobot. It's within an autonomous system, and obviously that fits into the higher level production environment to be able to schedule the delivery of the right fasteners to the right machine at the right time, and again at higher levels would relate to the quality and operational performance of such systems. So this is an autonomous mobile robot, a MIA. It's using laser scanning, so it's not following any tape on the ground. It follows its own path and can negotiate its way around obstacles, in its path as it goes, and reroute itself around them. Another example, just to touch on it briefly, we have some development facilities for a number of aspects of battery assembly, and one of them to show you here relates to again autonomous mobile robots, in this case being used to transfer battery modules between machines. So here's an example of a distributed manufacturing system where we've got a separate machine which is fed by an autonomous mobile robot, rather than being in a conventional production line. So we have a demonstration area for digitalisation Industry 4 training at WMG, and this shows an example of the sorts of, again, integrated technologies in the context of digitalisation. Moving on to quickly show you something around visualization and modeling. This is an example built using a gaming technology, using Unity, which shows a visualization of the same production system. And you can not only build 3D models and relate them to the physical system, but overlay dashboard information here, key performance indicators, perhaps select different views related to data analytics and what have you. So it enables you to have physical and virtual views of your production system, which can be used for remotely supporting the activity if you're feeding the real positional data of the systems through, for visualizing, doing what if analysis, or to help for support and maintenance examples for cases, for example. Yet another example to just show you quickly. I just show that this doesn't have to be just in the manufacturing a space of a traditional manufacturing plant. Here's an example where, with the AHDB, the Agriculture and Horticulture Development Board, we are looking at being able to improve the efficiency in horticulture, and this is transferring seed trays between different locations. So again, it shows the power and usefulness of digital modeling in being able to model and visualize use cases and evaluate them prior to the next phase of this project, which is building the physical autonomous mobile platform. So I hope those examples have given you some food for thought and insight into the work that we're doing. I wanted to finish off by just talking a little bit about, in the context of COVID-19 and the current situation. You've probably seen in the press, what's the role of Industry 4? Can it help make production systems more resilient? Etc. There are a large number of articles in the popular press for that. So how can this digital revolution help to address these wider challenges? I think some of that relates to having a larger amount of data and the interconnectivity between systems, and having in particular separate autonomous systems which are able to self-optimize and reconfigure, offers the opportunity for greater resilience, both within operations and across supply chains. So there's more opportunity for configurability and flexibility in such systems. Optimizing those systems can reduce their carbon footprint, and in a wider system of systems context, help to reduce waste by cross-relating a building with the factory machines within it, its air conditioning systems, its wider supply chains, and again, reusing, recycling, rebuilding, reconfiguring systems. They fit well into the realization of a broader circular economy, and indeed the products can be revisited in that context. So if we just look at some specific examples, I think how can these kind of capabilities help? Well, real-time visibility lets you understand the current situation. If you don't know the current situation, you can't react to it properly. AI and machine learning will and should allow you to reassess and replan efficiently once you have such systems robustly in place. Automation can get rid of those non-value add activities we talked about. Augmented and virtual reality can help workers to perform their jobs better, assist them where they may not have some of the skills. We show some examples that I showed of, digital models. You can use this and couple it with AR or VR to be able to offer, remote support and improve the availability of assets, which can be supported, from another part of the world, indeed, or another part of the country. So again, particularly in sort of current context, the enabling of such capabilities is important. Again, remote and virtual working, for remote maintenance and remote support in other ways, it goes hand in hand with that, using AR, VR and digital twins. You can locally manufacture, which gives you more self-sufficiency and flexibility. So additive manufacturing, and digital printing may then enable you to, whether that be spare parts or actually being flexibly being able to make the product locally is important, an important capability there to offer more resilience. Autonomous robotics, they can reduce the reliance on people. So in fact, we saw a system recently where, disinfecting robots and what have you, where an autonomous platform, somewhat like the ones we showed for our riveting systems, could be applied. It can assist where social distancing is a problem in the immediate context. And then maybe to finish in terms of future vision. I hope through what I've talked about, you can see it's very interdisciplinary. There are many interconnected systems and need for collaboration, that being both between the individual technologies, because the whole is much greater, offers much greater, value than the parts. And it's cross-sector. There's many different cross-sector applicabilities and commonalities that can be geared off, and there's the integration of IT, operational and IT technology. So openness in these systems and being able to promote dialogue across sectors, promoting joint understanding, systematic development of solutions which are not too vendor specific and are open, and in the broader sense of how factories fit with future cities and the energy systems. That system of systems will allow greater optimization in a collective sense to the benefit of all the subsystems, which in the context of perhaps net zero and sustainability will become more and more important, as well as offering the customer the ability to customize and have choice. So thank you very much for your attention, and I welcome your questions.
Okay, Robert, thank you very much. So before we throw the floor over to Tom and Heather, please, if you have any questions, put them into the questions box and such. I'd like to start off though, Robert, chairman's privilege and all that. You've worked around Europe and around the world, and we've been talking about this for a long time. Is the UK actually getting there fast enough, or do we need to make this transformation faster? And if so, what can we do about it?
Well, I think we're getting there, not as quickly as others, where perhaps the classic examples would be Germany, who are investing more and probably have a more stable and patient way of investing and supporting these kinds of technologies. I think on our side we are innovative. There are lots of new ideas and quite a lot of startups that are coming. I think in the context of our digital manufacturing centres like the catapults and other universities, there's an important role there in terms of training, both in educating the students with the relevant technologies and methods, and being able to bring people in from industry to help them and have exemplars of the technology. And then I think it's solving the right problems and encouraging our small and medium-sized technology partners to be able to help the larger companies. And I think on the side of initiatives like Made Smarter, which is starting to gain momentum now, to be able to help to engage constructively, solving the right problems. And I think, as I tried to show in some of my slides, have a phased approach, which isn't an ad hoc one, but builds, the capability progressively, and is appropriate to the, skills and the starting point for the companies which we're, engaging with.
Okay, and obviously, because of your background, you've taken examples from the sort of engineering side of the manufacturing industry, but I mean, everything you said is applicable to chemicals, from actually continuous stirred tank reactors through to extruders and all sorts of things that go on, isn't it?
Absolutely, yes. So you may have more continuous processes and less discrete products, but if you looked at battery manufacture, which is one of our areas there, it's very, very similar at the initial end, where you're optimizing processes and trying to reduce waste in that flow, be that batch or continuous processes. You want an insight through the data, that you're gaining from there to have real, actionable insights, as I mentioned, on that data, from that data. And it be agri-tech, food, chemicals, they're unit, although they may manifest themselves in slightly different ways, they're very similar problems in the way that this kind of technologies can add value.
Actually, to your point, I mean, a lot of chemical processes at the really front end are continuous stirred batch reactors, but they're moving towards continuous, plug and continuous flow processes, which of course require much more instantaneous correction of errors when they're going around. So the sort of system you're talking about is even more important to make it work.
Yes, I mean, I think the more real time you can get the processes, and the more you can push the the analytics to the edge. We working the tire manufacturer is another area that my group are involved in, and there you're looking at your batch manufacture of rubber in processes that then go to pond, go to discrete later on. But again, yeah, the same insights hold true. You want to instrument your processes, sufficiently and well enough to have the right insight, the right data, understand the behavior of those systems, and from that derive the value, be that in terms of maintenance of the system or optimization in terms of quality or to reduce waste.
Okay, so over to you. Is it Tom or Heather going first?
I've got on first. From Tim Reynolds. Do you see any unique challenges for successfully applying digitalization to large-scale chemical processes? For instance, are appropriate real-time sensor technologies available?
So I think I won't try and dodge the question, but obviously it depends on the process and the degree of control you would need to have to be able to make those decisions in real time. So not knowing the specifics of the process or a particular aspect of the field, obviously you shouldn't attempt to make real-time decisions unless you have appropriate sensors that can let you make those decisions correctly or have the confidence to do that. I guess in terms of the sensing technologies that are available, that may be an area where innovation is required. So if there is a deficiency in sensing technologies that are preventing that real-time insight, then that would be yet another area of innovation, would be the development of new sensing technologies. But I think it's obviously important to appraise that, look at the quality of the data you've got, understand the process, and then whether that's machine learning based and being able to infer information from a large data set, or being able to model more classically a process. It would depend on the the type of process, and therefore necessarily the type of sensing which would be needed, and hence are the right sensors available or not. I think that would be part of that process.
If I could just jump in there. I mean,
yeah.
when I started in the chemical industry, we measured temperatures, pressures, and flow rates. But over my time, I mean, I've seen infrared spectrometry used, remote resonance
Yes.
Raman, broadline NMR, and all sorts of tech. I mean, to the point you were making earlier in what's going on in the physical manufacturing side, the sophistication and the cheapness of modern sensors is what makes this really easy to do. And the great thing about chemistry is you can actually measure the process that's going on using the right chemical markers. So it really does lend itself to doing this very well indeed.
Right. So yeah, I mean, certainly would bear out what you've said in terms of the domains where we're looking. The dramatic reduction in sensor costs and the ability to do large amounts of processing, near the edge, close to the sensors, has sort of revolutionized the ability, whether that's using vision or other, sensing methods. It's become practical to do things that traditionally wouldn't have been thought possible.
Yeah. Okay, must be Tom's turn.
Yeah, thanks, Robert. So another question here from Wai Ming, who asks, do you have any ideas or suggestions for small to mid-sized factories if they are making small batches, such as home appliances? So the product range is wide, but if they're still hoping to implement Industrial 4.0.
So I guess it depends on their starting point, and do they want to collect basic data to understand, the variability in the production process, be that, throughputs and machine downtime and things like that. If they're easily done, and you'd connect a sensor setup to the individual machines and try and gain insight from that point of view. Vision systems, vibration sensors, can be added, and there are stages beyond that where you might go again with vision to more inspection of the product for its consistency, and so on. So you can build up a data set, and I guess it's starting, getting the basics right, working out what are some initial areas in the production process where you can add value or improve the quality, and then I think doing it in a constructive and consistent manner, so you can then consolidate and gain greater value through progressively integrating the information which you're gathering from perhaps those shop floor sensors with some information from your manufacturing execution system, if there is one, and the product traceability being introduced, so what went to which customer and when, how the batches relate to the quality, cross-relating information and making sure you have the right information to to gain those insights in a phased and coherent way.
So Heather again.
Thanks, Robert. So what changes does a business have to make, and what processes do they have to put in place before they can start to implement this digitalization?
So the business obviously needs to have an understanding of what's there already. So if it was a not a well-ordered activity and you didn't understand the phases of the process, and so some companies indeed might not benefit from digitalization until they basically get the fundamentals of the workflow and an understanding of the process flow and the product flow through their operations. Given that there's clarity of that, you can then say, well, is that paper-based? Can that progress to being digitized, and is that tracking products which traditionally weren't tracked in a digital manner? What information are we missing to be able to start to move on this journey? It obviously requires buy-in from the senior people, as well as the people on the shop floor, etc., who would need to understand why why are we doing this, for what purpose, and that it's a collective journey which has business benefits, and trying to articulate the potential business value from this as well, so that it's not, you're not aimlessly going into it and adding some sensors and a 3D visualization of your system. You're saying what are the specific gains I can make, and how does that relate to either added value, increased quality, offering the customer more choice, being able to add value in the supply chain by being able to connect better to my supply chain partner. So I know with companies like Ford, where we've worked in the past, there would be digital modeling and connectivity for some of the partners, but some of the partners making some of the simpler equipment would have no digitalization or digital designs of their products, and being able to integrate those and enable them to share information, greatly kind of added value and opened up their market to be more diverse, so they weren't just locked into one supplier, that they could, if you like, promote what they were doing in a wider marketplace.
Okay, Tom.
Thank you. Another question here from John Carberry, who asks, how do you see 5G impacting smart factories? Okay,
so we've done some initial studies and there's a lot of interest in it, and one of the variants of 5G is there to kind of offer the concept of the machines are less connected, you can move them around more, it frees you from wired networks while still having a high level of throughput. So it's improving the configurability of the systems through having that high bandwidth available. So that could give you more freedom, and maybe in the context of aerospace, for example, you would be able to have much more mobile configurable platforms which could make use of the data. There's another mode of 5G which is for I guess chemical plants and field networks, where you've got many sensors, but you've got small amounts of data coming from those in a broader context. So that might be used in the chemical industry, for example, in refineries or in that context. In the sort of high value manufacturing, data intensive systems, I think it's offering that freedom to to decouple and have truly mobile autonomous systems while still having an integration of the data from these devices.
Okay, Heather, any more?
Yeah, I have another question. So you mentioned that managers are sort of hesitant to implement this because they want to see it work in other businesses first. And I was wondering, yes, is cybersecurity also a major concern there?
So cybersecurity is a major concern, and trust as well, more generally, in respecting IP and value is if I kind of elaborate on that. So good cybersecurity is obviously fundamental to the way such systems should be built and the infrastructures which it's built upon. I think they're kind of, whether it's blockchain or other methods, there's also the issues of, if all this digital information is available, then it makes my product either easy to copy, or indeed the business transaction at the moment you may be comfortable with it because there isn't digital data associated with it. So these are kind of disruptive aspects where, given you've got the cybersecurity, and obviously that's a must, and there are more and more examples have emerged of systems being hacked and abused, and whether that ransomware or malfunctions in systems being caused maliciously. There's that, and then there's what's the new business model for the kind of supply chain to operate in this way, where more sharing of information occurs, and visibility of that, ownership of that, and clarity and trust in that partnership, which is, I guess, moving from the old forms of partnership and trust to a digitalized one becomes very important.
Okay, I think we've had our time. So Robert, I'd like to thank you again for an excellent talk, covering all sorts of things with its usual sort of breadth and depth. For those of you who have any more questions, Robert has been careless enough to leave his email on the screen for the last 20 minutes, so you can chase him down, or if you have any questions about the work we're doing in the SCI in this area, just contact us.
We're very happy to do that and engage with people afterwards.
Yeah, thank you very much, Robert.